Okay. All the introductory part of the model 1 we have discussed in the first session. So today we will go with the analysis of a PSC member. Okay, analysis of PSC member. Analysis means here we will be studying how to find the stresses. Okay, stresses in a beam when it is subjected to external load, and it will also have its own weight, correct? And pre-stressing force will also be there. Okay, considering all these forces, how to find the resultant stresses that is acting on the beam, that will be learning in the coming sessions. Okay, so before going to start actual analysis problems, I want to discuss the very important concept of PSE, that is resultant stresses at a section. It is very important, students. Please listen and understand it clearly. If you understand this clearly, then only you will be able to solve the analysis problems. Okay. So write the headline as resultant stresses at a section. Write the headline as resultant stresses at a section. Resultant stresses at a section. Please don't simply listen to the class. Uh, have a separate notebook for this particular subject, and keep writing all the important things that will be discussed in the sessions. Okay. Now let us study how to find the resultant stresses of a beam subjected to some external load and subjected to some pre-stresses or pre-stressing force. Okay. So if you understand this, then you will be able to solve the problems. You will be able to find the resultant stresses for a realistic problems. Okay. For that, we'll consider a beam. Okay. We'll consider a beam. Okay, beam subjected to some live load, and there will be self weight of the beam also, correct? Or dead load of the beam as well. We'll consider some live load on the beam. Let us call it as Q per unit length. Okay, I'm assuming intensity of the live load as Q per unit length. Let me draw the centroidal axis of the beam. Okay, for the same beam, assume that there is some pre-stressing in the beam. Okay. Okay, let us assume the pre-stressing force as P. Okay. Pre-stressing force as P. Let us take L as length of the beam. L as length of the beam. Okay. Now, for this beam, we will find resultant stresses. Okay. Here, the resultant stresses means resultant stresses means combination of pre-stresses and dead load stresses, dead load stresses, and one more, live load stresses. Okay, the beam will be subjected to three main kind of stresses here. One is stresses due to pre-stressing force, that is called as pre-stresses. Okay, the stresses induced in the beam due to pre-stressing force called as pre-stresses. Then there are stresses induced due to self weight of the beam or its own weight, correct? That is called as dead load stresses, and stresses induced in the beam due to live load, that is acting on the beam. Okay, if you find pre-stresses, that is stress due to pre-stressing force, and dead load stresses and live load stresses, adding all together, you can find what is the resultant stressor, the resultant stress that is acting on a beam at required location, whether it may be top fiber or the bottom fiber. Okay, whether it may be top fiber or the bottom fiber. Now what we will do, we will find each and every stresses individually, then we will add all the stresses to get the resultant stress. Okay, first we will find pre-stresses. Okay, pre-stresses. Okay, we'll find the expression for the pre-stresses, that is stress due to pre-stressing force. Okay, now here we can see the pre-stressing force is acting at an eccentricity E from the neutral axis or the central axis of the beam. Correct? Huh? The pre-stressing force is acting at a eccentricity of E from the neutral axis. Okay. You just look into the loading condition of the beam. Okay. Just tell me what will be the nature of bending of the beam due to this pre-stressing force. What will be the nature of bending of beam? Whether it will be a hugging moment or sagging of the beam. You please reply. Anyone? What will be the nature of bending of the beam? Whether it will be hugging bending, whether beam will be in hugging or sagging. Anyone can reply. See, there is a pre-stressing force which is acting below the neutral axis. That is at an eccentricity E from the neutral axis. Due to this pre-stressing force, what will be the nature of bending of the beam? It will be hugging or sagging? It will be
Sagging, sir.
hugging. Yes, yes.
Sagging, sir.
Yes, hugging. Correct. The beam will be in hugging like this. Correct. So this, due to this pre-stressing force, as the beam undergoes hugging bending moment, okay, the top fiber, you can see the top fiber will be subjected to tensile stresses, and the bottom fiber will be subjected to compressive stresses. Okay, the top fiber is subjected to tensile stresses and bottom fiber is subjected to compressive stresses. Okay, now let me tell the notation or the sign convention for pre-stress concrete structures. Okay, with respect to the stresses, I'm telling the compressive stress. Okay, the compressive stress is represented by positive sign. Similarly, the tensile stress is represented by negative sign. Remember, students, this is a sign convention which we have to use for PSC. Okay, compressive stress is represented by positive sign, tensile stress is represented by negative sign. Okay, now we came to know that due to this pre-stressing force, the beam undergoes hogging bending moment, and the bottom fiber of the beam is subjected to compressive stresses, and top fiber of the beam is subjected to tensile stresses. Okay. Now coming to the type of stresses caused by this prestressing force. Okay, coming to the type of stresses caused by this prestressing force, there are two main type of stresses. One is direct stresses. One is direct stresses. Direct stress means what? It is directly the load by cross-sectional area of the beam. If you assume some cross-section of the beam, okay, if you assume some cross-section of the beam, the direct stresses due to prestressing force P is directly P by A. Okay. Along with that, this prestressing force will also cause the bending stresses. It will also cause the bending stresses at both the top and bottom fiber, bending stresses. Okay, that is represented by PE by Z. Remember, P into E means what? It is force into distance. Force into distance is nothing but moment. Okay, that moment divided by the section modulus of the cross section of the beam will give bending stresses due to this prestressing force. Okay, the PE by Z is the bending stresses due to prestressing force. Okay, so we came to know the direct stresses and bending stresses due to prestressing force. This same we can draw in a stress distribution diagram. Okay, stress distribution diagram. I'll write the stress distribution diagram for the same case. Okay. Here I'll write. So as I said, there are two kinds of stresses, direct stresses and bending stresses. Okay. The direct stress, now I'll write distribution of the direct stress due to prestressing force. Okay. So what about the direct stress? Direct stress in all points along the depth of the beam, the direct stress is compressive only. It is compressive stress only. Okay. Here you can see the prestressing force P is applied towards the beam. When it is applied towards the beam, then it will cause compressive stress throughout the depth of the beam. So even in the top fiber, the nature of stress due to prestressing force. Okay, nature of direct stress due to prestressing force will be compressive only, and even in the bottom fiber, it will be compressive stress only. Okay, therefore, it will be positive on both sides. Positive on both sides. So, what is the amount of direct stress caused? It is P by A. P by A. Okay. Now, there is one more stress, that is bending stress due to prestressing force P, that is PE by Z. This bending stress, here I have written the nature of bending of the beam. The bottom fiber is subjected to compressive stresses, top fiber is subjected to tensile stresses. Now, I'll write the diagram. So the bottom fiber, it is subjected to compressive stress. Compressive stress is represented by positive sign. Positive sign means on right of the reference line. Okay. What is the amount of stress caused? It is P by Z. P by Z. Okay. Plus P by Z. Okay. And in the top fiber, there is tensile stress. Tensile stress is represented by negative sign. Negative sign means on left side of the reference line. On left side of the reference line. Okay. Now joining both the points, we will get stress distribution of bending stress due to prestressing force. Here it will be minus PE by Z. Understood, students? Now we have written stresses due to pre-stressing force. This is pre-stresses. Okay. Now we have determined nature of stress distribution due to the pre-stressing force P. Okay. Now first one is over. Now we'll move on to the next type of stress. Second type of stress. What is the second type of stress? It is dead load stress. Okay. It is dead load stresses. Dead load stresses. Dead load stresses. Dead load stresses. How we will find the dead load stresses, students? First, let me know what is the nature of bending of the beam due to dead load, whether it is sagging or hugging. What is the nature of bending due to the dead load of the beam? Please be interactive, students. Please reply. Whatever the answer you get, you please reply. What will be the nature of bending moment due to dead load, due to its own weight? Sagging or hugging?
Sagging.
Yes. It will be sagging or hugging. Anyone can reply.
Sagging.
Yes, it will be sagging. Okay. Now, the nature of bending moment or bending of the beam is sagging. Like this. It will be sagging. So in this case, the top fiber is subjected to compressive stresses, stress, and the bottom fiber is subjected to tensile stress. Okay. Now the question is how to find the dead load stresses. Correct? How to find the dead load stresses. Dead load stresses are determined by using dead load moment. Okay. What is moment due to dead load? Dead load moment is given by the formula WL square by 8. WL square by 8 or WD. Instead of writing W, I'll write WD, which represent dead load weight. WD L square by 8, where WD is the intensity of dead load of the beam. Okay, this dead load we can easily calculate. If you know the cross section multiplied by density of the concrete will give dead load, and WL square by 8. If you assume the nature of support as simply supported beam, so the moment due to dead load will be WL square by 8. Okay, moment due to dead load will be WL square by 8. I'll denote it as mg. Okay, moment due to dead load, I will denote it as mg. If you know the dead load moment, you can find the stresses due to dead load moment. Okay, stresses due to dead load or dead load moment. Similar to this bending stresses due to prestressing force. Okay, just you need to divide by section modulus mg by z. mg by z. Okay, so you by using this formula, okay, dividing the moment due to dead load by the section modulus of the beam, we will get stresses due to dead load. So if I write the nature of stress distribution due to dead load stresses, what will be the nature of stress distribution? As I said, top fiber is subjected to compressive stress. Compressive stress is represented by positive sign. So on the right side of the reference line. Okay. So the amount quantity of stresses is or magnitude of the stresses is mg by z. Okay. Then on bottom fiber tensile stresses negative sign. So on the left side of the reference line. So this is the nature of stress distribution due to dead load stresses. This is mg by z. So here it is positive, it is negative. Okay. So this is how we find the stress distribution due to dead load of the beam. Similarly, if you write live load stresses stress distribution, okay, live load stresses. Third one is remaining is live load stresses that are do now. Live load stresses, live load stresses, live load stresses. Similar to the dead load stresses, we will find the live load stresses. Okay, first you need to find live load moment. Live load moment. Okay, I will represent live load moment as MQ because I have taken intensity of load as Q per unit length. Okay, MQ will be WQ L square by 8. WQ L square by 8. So here also I will change the notation. MG I will write as WG L square by 8. WG means intensity of the dead load. Okay, WQL square by 8. If you get the live load moment, you can find the stresses due to live load moment or stresses due to the live load. So the stresses due to live load is given by MQ by Z. MQ by Z. And what about the nature of bending moment due to live load moment or due to live load? So it is a uniformly distributed load acting on the beam. So due to that live load, again there will be sagging bending moment of the beam. Okay, there will be sagging of the beam. So here compressive stresses, positive sign, tensile stresses, negative sign. So what are the nature of stresses? Stress distribution you got for dead load, same nature of stress distribution you will get. Only the difference is here you are going to consider dead load moment, here you are going to consider live load moment. That is the difference. Okay, if I write the stress distribution, so top fiber compressive stresses positive sign, bottom fiber tensile stresses negative sign, joining you will get the stress distribution. Okay, so here MQ by Z, MG by Z. Okay, so here it is positive and negative. Okay, and coming to this Z, okay, coming to this Z or it is section modulus. See, if the with respect to this section modulus value, no, if the figure is symmetric about the x-axis, okay, if the figure is symmetric about the x-axis means if this x-axis dividing the figure into two equal parts, this section modulus will be same at both top fiber and bottom fiber. Section modulus with respect to top fiber and bottom fiber will be the same. If you have a section which is not symmetric about x-axis, okay, in that case you will have different section modulus. You will get different section modulus with respect to top fiber. Top fiber you will get different section modulus with respect to bottom fiber. Okay, therefore here I'll write ZT, ZT and ZB. Here also ZT and ZB. Then ZT and ZB. Okay. Here, whatever the section we have considered for this beam is rectangular, no problem. For rectangular beam, the ZT is equal to ZB is equal to Z. Okay, both will be the same, both values. But if a figure is not symmetric about the x-axis, then you will have different section modulus values with respect to top fiber and the bottom fiber. While doing the actual numerical problems, so you will understand in a clear way. Okay. Now we have determined all the stresses, that is stresses due to prestressing force, you have determined stresses due to dead load, stresses due to lay load. Now the next step is to add all the stresses to get the resultant stress that is acting on the beam. Okay, now I'll write the resultant stress distribution diagram. First I'll write the cross section. I'll write the cross section. Okay, cross section. Okay, so if you write the cross section, here we have the tendon. Okay, this is the tendon. Okay, this is the tendon. So in the cross section, you will be able to see the diameter of the tendon, or diameter of the pre-stressing wire, or diameter of the cable. You will be able to see diameter of the cable or diameter of the tendon. Okay. Now we will start writing all the stress distribution diagrams. So for the stresses due to pre-stressing force, there are two kinds of stresses. One is direct stress and one more is bending stress. I'll write both the diagrams here. This is stress due to direct stress. Okay, P by A, P by A. Okay, then there is one more kind of stress, that is bending stress. Bending stress, nature of stress distribution is minus and plus. Minus plus. So direct stress will be having positive sign on both sides because nature of stress is compressive stress throughout the depth of the section. So here what is the value? P by ZT, PE by ZT, then PE by ZB. Okay. Now I'll write stress distribution due to dead load stress plus or minus here mg by ZT, mg by ZB. Then finally stresses due to live load. Same kind of figure. Okay, positive, negative, mq by ZT, mg by ZB. Okay, so adding all stresses, okay, that is stress due to direct stress due to pre-stressing force, okay, and bending stresses due to pre-stressing force, and bending stresses due to dead load, and bending stresses due to live load, we will get a resultant stress distribution diagram. Okay, we will get resultant stress distribution diagram. Let me write the resultant stress distribution diagram. Okay, so here what will be the value? Resultant stress distribution. Here value will be sum of P by A minus PE by ZT, then plus mg by ZT plus mq by ZT. Okay. So in the bottom figure, what is the resultant stress? It will be sum of P by A, then plus PE by ZT, then minus mg by z. So it is zb, then minus m cube. This is cube minus m cube by zb. So this is what the resultant stress. Okay. And the nature of stress distribution in the resultant stress diagram will be, it varies depending upon the pre-stressing force, depending upon the cross section, depending upon the section modulus value. This will vary. Okay, it will not be as same as whatever I have written. Okay, I have written an approximate diagram. When a numerical value is given in the problem, then you can guess what is the actual nature of resultant stresses. Okay. Now this is the stress distribution. These two diagrams indicate stress distribution due to pre-stresses or pre-stressing force, which is simply called as pre-stresses. Pre-stresses. Then this diagram indicate dead load stress, dead load stresses, and this diagram indicates live load stresses, and this final diagram is resultant stresses. Okay, so this is how we find the resultant stresses at a section of a pre-stressed concrete beam or any other element. Okay, I hope this is clear for you all. Still, if you have any doubts on this concept, we can ask students before moving on to the numerical problems. I hope this is clear for everyone. So I will move on to the problems. Okay. So here the respective values will be given. That's it. Lay load on the beam will be given. Cross section of the beam will be given. Okay. The magnitude of the pre-stressing force will be given. Just substitution and getting the answer. That's it. Okay. To solve the problems. Okay. All the numerical values of all these things will be given. Just you need to calculate and you need to draw the resultant stress distribution diagram. Okay, that is what will be there in the problems. Okay, let us solve the first problem. Okay, first problem. All of you please write this problem. Is it visible, students? The problem. Are you able to read the problem, students?
Yes, sir.
Okay, thank you. Please write the problem. I'll dictate it. A rectangular concrete beam. Please write a rectangular concrete beam. Rectangular concrete beam of cross section 30 centimeter deep. Of cross section 30 centimeter deep and 20 centimeter wide. 20 centimeter wide is pre-stressed by means of 15 wires of 5 mm diameter. 15 wires of 5 mm diameter located 6.5 centimeter from the bottom. 6.5 centimeter from the bottom of the beam and 3 wires of diameter of 5 mm. 3 wires of diameter of 5 mm, comma 2.5 centimeter from the top. 3 wires of diameter 5 mm, comma 2.5 centimeter from the top. Full point. Assuming the pre-stress in the steel as Assuming the pre-stress in the steel as 840 Newton per mm square. 840 Newton per mm square. Calculate the stresses at the extreme fibers. Stresses at the extreme fibers. Extreme fibers of the midspan section. The midspan section. When the beam is supporting its own weight over a span of 6 meter. Over a span of 6 meter. Point. If a uniformly distributed live load, of 6 kilonewton per meter is imposed, evaluate the maximum working stress. In concrete. Full point. The density of concrete is 24 kilonewton per meter cube. 24 kilonewton per meter cube. Okay. All of you just go through the problem. All required data is given. A rectangular concrete beam of cross section 30 centimeter deep and 20 centimeter wide. Let me write the figure for the same. Okay. Solution. Okay. A rectangular concrete beam of cross section 30 centimeter deep and 20 centimeter wide. The depth of the beam is given. D is given as 30 centimeter. In terms of millimeter, it is 300 millimeter. And width of the beam is given as 20 centimeter. In terms of millimeter, it is 200 millimeter. Okay. So I'll write the cross section as 300 by 200. 300 by 200. Okay. Is pre-stressed by means of 15 wires of 5 mm diameter located 6.5 centimeter from the bottom of the beam. Okay. He is saying that there are 15 pre-stressing wires or 15 cables or 15 tendons having 5 mm diameter located 6.5 centimeter from the bottom of the beam. Now I'll write figure for the same. 15 numbers, no? 15 numbers means 1, 2, 3, 4, 5, 6, 7, 8, and at the top 1, 2, 3, 4, 5, 6, 7. Okay. Okay. So 15 numbers and they are placed, their centroid is located at 6.5 centimeter from the bottom. Okay. 6.5 centimeter means 65 mm. 65 mm. Okay. Next, Continue to read the problem. And 3 wires of diameter 5 mm, 2.5 centimeter from the bottom, from the top. Okay, there are only 3 number of wires. 3 number of wires. Okay, having diameter 5 mm, and they are located at a distance of 2.5 centimeter, means around 25 mm from the top. Okay, assuming pre-stress in the steel as 840 Newton per mm square. Pre-stress in the steel is given. It is how much given? Pre-stress in the steel, just write in the given data. Pre-stress in the steel. Pre-stress in the steel is how much? 840 Newton per mm square. 840 Newton per mm square. Calculate the stresses at the extreme fibers of the midspan section. When the beam is supporting its own weight over a span of 6 meter, length of the beam is 6 meter. Then, if a uniformly distributed live load of 6 kN per meter is imposed, evaluate the maximum working stress in the concrete. Okay, the total length of the beam is how much? Total length of the beam is 6 meter. Then live load on the beam is given. UDL on the beam is given. What is the intensity of the UDL given? Intensity of the UDL given is how much? 6 kilonewton per meter. Okay, and density of the concrete is also given. Density of concrete is given as 24 kilonewton per meter cube. Okay, length of the beam is 6 meter. L is 6 meter. Okay, and the live load given is WQ is 6 kilonewton per meter. So this is what the given data in the problem. Okay, this is the given data in the problem. Okay. Now, the first step is to find or to locate centroid of the pre-stressing force. Okay. Now, first step is to locate centroid of the pre-stressing force. Okay. Here in the problem, he is saying that there are few bars provided at the bottom of the beam, and there are few pre-stressing wires provided at the top of the beam. Okay. So both bottom bars and top bars, they are carrying some pre-stressing force. Correct? Both the top bars and bottom bars, they are carrying some pre-stressing force. Now, the first step is to find the centroid of the pre-stressing force. Okay, centroid of the pre-stressing force. Okay, so we will find centroid of the pre-stressing force. Below, right? Distance of centroid of I'll tell you why this centroid of the pre-stressing force is required in the next coming calculation. Okay, distance of centroid of pre-stressing force from base. Okay, from bottom of the beam we will locate distance of centroid of pre-stressing force. Okay, distance of centroid of pre-stressing force. Let me call it as y. Let me call it as y. Okay. So here there are two kinds of means the wire having 5 mm diameter. It is provided at two places, at bottom and the top. Correct? At bottom and the top. Now we have to look at centroid of the this pre-stressing force or pre-stressing wires. Okay, for that we'll the formula will be A1 Y1 plus A2 Y2 divided by A1 plus A2. Okay, where A1 is area of the bottom bars Okay, that will calculate down A1 is equal to area of bottom bars, bottom wires. Okay, how will find the area of bottom wires? See, diameter of the bar is given. Okay, diameter of the bar is given as 5 mm. Okay, in the problem it is mentioned 5 mm. Okay, 5 mm diameter, and number of bars at the bottom is 15 numbers. Okay, now first what you do is you find area of one bar. Area of one bar will be pi d square by 4, pi into 5 square by 4 multiplied by number of bars. Number of bars at the bottom is 15. Number of bars at the bottom is 15. So area of one bar multiplied by number of bars will give total area of the bottom bars. Okay. So if you calculate the answer, you will get 294.52 mm square. All of you, please check the answers. Okay, if you are getting any other different answer, let me know. Okay, we will do the correction. Okay, don't simply write the answer which I am writing here. You please cross check. Please do the calculation of your own and cross check the answer. Then A2 is area of top wires. Area of top wires. Area of top wires. At the top, he says that there are three number of bars having diameter of 5 mm located at some distance of 25 mm from the top. Okay. So diameter is same here. Pi into pi square divided by 4 into number of bars is 3. Okay. Please check the answer. Answer is 58.90 mm square. Okay. Then A1, A2 we have calculated. The remaining terms are Y1 and Y2. Y1 and Y2. Y1 and Y2 is nothing but distance of centroid of bottom bar. Y1, I am telling, distance of centroid of bottom bar from the base of the section or base of the rectangle. It is directly 65 mm. Y1 is directly 65 mm. Similarly, Y2 is distance of centroid of top bars from the base again, not from the top. We are calculating or we are locating distance of centroid of prestressing force from the base. So all the value should be written with respect to base only. Okay. So here Y2 is distance of centroid of top bars from the base. Overall depth is how much? Overall depth is I think the cross section dimensions are written reverse way, correct? Na? So I'll make the correction here. It is 200, okay, 300 deep and 200 wide. 30 centimeter deep and 20 centimeter wide. So this becomes 300. So this will be 200 and this will be 300 overall depth. Okay. Now Y2 as I said, Y2 is the distance of centroid of the top bars from the base of the rectangle. Overall depth is known. Overall depth is 300. 300 minus 25 if you do, you will get Y2. Okay. Distance of centroid of top bars from the bottom you will get. Overall depth minus 25 if you do, you will get Y2. Y2 is 300 is the overall depth minus 25. How much you will get? 275 mm. 275 mm from bottom. From bottom. Okay. Now substituting all the values, you will get y is equal to a1 y1 294.52 into y1 65 plus a2 y2 58.9 into 275 divided by a1 plus a2. 294.52 plus 58.9. Okay. Please calculate the answer. Okay. And you check the answer as well. It is 100 mm. Y is equal to 100 mm. Y is equal to 100 mm. Now, the distance of centroid of prestressing force. Okay, the distance of centroid of prestressing force. Let me write the centroidal axis for the beam. Now we have calculated distance of centroid of the prestressing force from the base. How much we got? We got it as 100 mm. Okay, 100 mm means somewhere here we will get it. Somewhere here. So this is at this location, means at a distance of 100 mm we have the centroid of the prestressing force or resultant of the prestressing force which acts on the section. Okay. And what about the distance of the neutral axis from the base or centroidal axis of from the base? Distance of the centroidal axis from the base is how much? It is 150. Correct? Huh? Total depth divided by 2. Total depth divided by 2. So using both these two data, you can calculate eccentricity of the prestressing force. Okay, which is nothing but distance between the neutral axis or distance of resultant of prestressing force from the neutral axis or the centroidal axis. Say for this rectangle, both neutral axis and the centroidal axis are the same. Okay, so using these two 150 and 100 mm, you can calculate the eccentricity. Eccentricity is nothing but distance of centroid of the prestressing force from the neutral axis. Okay. See, these bars, no, instead of giving on both sides, if any one side, if these bars are given, no need of finding centroid of the prestressing force. Okay. Only the bottom bars are given, it will be directly 150 minus 65. Okay. So from here to here, there will be eccentricity. As the bars are given on both top and bottom, then you need to find the resultant prestressing. You need to locate the resultant prestressing force. Okay, resultant of the prestressing force, as we have done just before. Okay, it is located at a distance of 100 mm. Therefore, we can find the eccentricity now. Therefore, eccentricity is given by eccentricity is equal to, from the figure we can calculate 150 minus 100. 150 minus 100, you will get 50 mm as eccentricity. Okay, so eccentricity is 50 mm. Okay, now pre-stresses is given. Okay, pre-stress in the steel is given. Okay, that the stress which is acting in the wires is given. How much it is given? It is given as 840 Newton per mm square. Using this data, you can calculate amount of or magnitude of the pre-stressing force acting on the wire, acting along the wire. Therefore, the pre-stressing force P is equal to, what is force? What is force? Force is stress into area, correct? Stress into area. Stress is equal to force by area, therefore force is equal to stress into area. Stress in the wires is given. How much it is given? 840. Okay, and area of the wires you can calculate. Okay, it will be 294 plus 294.52 plus 58.9 will give total area of the bars. Okay, therefore prestressing force P is equal to stress into total area of wires. Total area of wires. Okay, So P is equal to stress in the wires is how much? It is 840. It is 840 into total area of wires. Area of bottom bar is 294.52 plus 58.9. 294. Okay, suddenly internet connection was happened. We'll continue. Okay, screen is visible. Let me know. Screen is visible, students.
Yes, sir.
Okay, okay. So the answer is 296.8 into 10 power 3. You might have got the answer already. Check it. 296.8 into 10 power 3 Newton is the prestressing force. Okay. Now, in the previous case, we have seen P by A, P by ZT, mg by ZT, correct now? So now we got prestressing force. Okay. Next, what is required? Area of cross section of the beam is required, that you calculate now. Area of cross section. Area of cross section. A is equal to, it is just B into D, width into depth, 200 by 300. What is the answer that you get? You will get 60,000 mm square. 60,000 mm square. Then what else is required? You need the value of Z, no? P by A is more. P we have calculated, A we have calculated, eccentricity also we have calculated. Then what you need? You need a section modulus value, correct? Section modulus Z is, how it is calculated? Section modulus. It is the ratio of moment of inertia to that of uh, the distance of neutral axis from top fiber or the bottom fiber. Okay. So here it is a rectangle. Okay. It is a rectangle. The neutral axis and central axis both will be the same. So Z will be same for both top fiber and the bottom fiber. So instead of representing separately by ZT and ZB, I'll directly take it as Z because it will be same for both top fiber and bottom fiber figure because it is symmetric about X axis. This I explained earlier. Okay. Now section modulus ZT is equal to ZB is equal to Z. Okay, it will be same. It will be I by Y ratio of moment of inertia to that of distance of neutral axis from either from the top fiber or the bottom fiber. Okay, so distance of centroid of prestressing force. I'm sorry, distance of centroid of prestressing force either from the top fiber or the bottom fiber. Okay, I by Y. Y is equal to here. This is the rectangle. It is symmetric about X axis. Okay, so Y will be directly equal to D by 2. Okay, I'm sorry, this Y is nothing but the distance of centroidal axis from top fiber or the bottom fiber. Okay, whatever the Y we have calculated before, okay, this Y is distance of centroid of pre-stressing force from the bottom fiber. Okay, this Y, distance of centroid of pre-stressing force from the bottom fiber. Now, whatever the Y which is required to calculate the section modulus is the distance of centroid of the section either from the top fiber or the bottom fiber. Okay, so this is the centroidal axis XX. So it will be at a distance of D by 2 and D by 2 from either top fiber or the bottom fiber. Therefore, as this central distance from top fiber and bottom fiber is same, that is D by 2, then ZT is equal to ZB is equal to Z. Y is equal to directly D by 2. D is how much? D is 300 divided by 2, nothing but 150 mm. Okay, 150 mm. Okay, so why you got moment of inertia you can calculate for rectangular section it is BDQ by 12. BDQ by 12. B is 200 into depth is 300 Q by 12. I is equal to moment of inertia. How much you will get? Check the answer. That is 450 into 10 power 6 mm raised to 4. This is what the moment of inertia value you get. Okay, now you can calculate the section modulus. Therefore, section modulus Z is equal to I by Y. I is 450 into 10 power 6 divided by Y is 150. Okay, Z is equal to how much you will get? It will be 3 into 10 power 6. What is the unit for section modulus? It is mm cube. 3 into 10 power 6 mm cube. Okay. Now you got section modulus as well. What else is required? Other than section modulus, you need mg and mq now. Mg is moment due to dead load. Mq is moment due to live load. Those things also are also required. First, we will calculate moment due to dead load. Mg we will calculate. Moment due to dead load. Moment due to dead load. That is mg. Okay, mg. So moment due to dead load is given by Wg L square by 8. Wg is nothing but self weight of the beam. First you calculate that self weight. Self weight of beam is equal to, how will calculate the self weight of the beam? Cross sectional area multiplied by density will give self weight of the beam. Correct? Cross-sectional area multiplied by density. Cross-sectional area multiplied by density will give load per meter length, intensity of the cell weight or dead load. Okay, so cross-sectional area we have already determined it is 60,000 mm square. And one more important thing here, students, you can see the density. Okay, the density is given in terms of kilonewton per meter cube. Okay, kilonewton per meter cube. So density is in terms of kilonewton per meter cube. So here while finding the cross-sectional area, you find the cross-sectional area in terms of meter square only. This is very important. Okay, 0.200 mm is 0.2 meter, 300 mm is 0.3 meter. Okay, so this is important. Remember, don't forget here. If it's substitute in mm, then answer will go wrong. Into density is 24 kilonewton per meter cube. Okay, therefore the self weight of the beam Wg, if you calculate, you will get the answer as 1.44 kilonewton per meter. 1.44 kilonewton per meter. Okay, therefore we can calculate self weight moment or the dead load moment. Therefore self weight moment or dead load moment is given by mq is equal to wq, sorry, mg is equal to wg l square by 8. So wg is 1.44 into length of the beam is how much? Length of the beam is given as 6 meter. 6 square by 8. Okay, if you calculate the moment mg, you will get it as 8.4, sorry, 6.48 kilonewton meter. In terms of Newton millimeter, it will be 6.48 into 10 power 6 Newton millimeter. Okay. Now self weight moment is over. Finally, we require one more data, that is MQ. MQ is what? It is live load moment. Okay, live load moment. Live load moment MQ. Okay, live load moment MQ is directly what? WQ L square by 8. Intensity of the live load is given. Intensity of the live load is how much it is given? WQ, it is 6 kilonewton per meter. 6 kilonewton per meter. Therefore, it is 6 into 6 square by 8. Answer is 27 kilonewton meter. Okay. Live load intensity is 6 kilonewton per meter, acting over a length of 6 meter. So moment due to live load is W square by 8, that is 27 kilonewton meter. Now all the required parameters to calculate the stresses is over. Okay. Prestressing force, area, eccentricity, section modulus, moment due to dead load, moment due to live load, all are calculated. Just you calculate the stresses directly by using this formula P by A, PE by ZT, mg by ZT, and mq by Z. Okay. Now I will calculate one by one. Direct stress due to prestress. First one. Direct stress due to prestress, which is P by A. Okay. What is P here? Prestressing force. P is nothing but prestressing force that we have calculated 296.8 into 10 power 3. 296.8 into 10 power 3 divided by area of cross section 60,000. Answer, you check the answer, please check the answer. Don't simply write the answer which I am writing here. Cross check. If you are getting any other different answer, let me know. Next, what is the next type of stress? Bending stress due to prestresses. Bending stress due to prestressing force. bending stress due to prestressing force, which is given by what? P by Z. Okay. ZT and ZB are same. I'll just take it as P by Z. Okay. P by Z. P by Z. So prestressing force P is 296.8 into 10 power 3. What is the eccentricity value we got? We got eccentricity as 50 mm divided by section modulus value. How much we got? It is 3 into 10 power 6 into 3 into 10 power 6. Answer, if you calculate, you will get 4.95 Newton per mm square. Okay. What next? What is the third type of stress? Stresses due to self-weight. Stress due to self-weight. Stress due to self-weight, that is mg by z. Moment due to dead load divided by section modulus. Moment due to dead load is how much? mg 6.48 into 10 power 6. 6.48 into 10 power 6 divided by 3 into 10 power 6. Okay, 3 into 10 power 6. So this MQ, I'll write in terms of Newton millimeter, 27 into 10 power 6 Newton millimeter. Okay, so the stress due to self-weight, if you calculate, you will get 2.16 Newton per mm square. 2.16 Newton per mm square. Then stress due to live load, lastly. Stress due to live load, which is mq by z. Stress to moment due to live load is 27 into 10 power 6. 27 into 10 power 6 divided by 3 into 10 power 6. So the answer is 9 Newton per mm square. Answer is 9 Newton per mm square. Knowing all the stresses, now you can calculate resultant stress, correct? You can easily calculate resultant stress. Therefore, resultant stress will be, resultant stress at top fiber is how much? What is the formula? At top fiber it is P by A minus PE by ZT plus mg by ZT plus mq by ZT. Okay. Resultant stresses, you write the resultant as resultant stresses. Therefore, resultant stresses. Now you can calculate at top fiber it is P by A minus PE by Z plus mg by Z plus mq by Z. It is actually it is T, but here we have ZT is equal to ZB is equal to Z only. So in terms of in place of ZT, you will take Z only, those with the Z values only. That we have already calculated here. So P by A is 4.95, PE by Z is 4.95. So it is 4.95 minus 4.95 plus mg by z is 2.16. 2.16. Then mq by z is 9 plus 9. Just calculate. You will get the resultant stress as 11.16 Newton per mm square. 11.16 Newton per mm square. Similarly, at bottom fiber, this is at top fiber. At bottom, only the sign will vary, P by A, except the first term. For P by A, it will be positive only. Plus PE by ZT minus mg by ZT minus mq by ZT. So it will be 4.95 plus 4.95 minus 2.16 minus 9. The answer is minus 1.26 Newton per mm square. Okay, minus 1.26 Newton per mm square. What this plus sign indicates? Nature of stresses at top is compressive. Okay, compressive stresses are represented by plus sign. Here you got the answer in terms of negative sign, which represents tensile stresses. Tensile stresses. Okay, it represents tensile stresses. Okay, now you can write the final stress distribution diagram. The same diagram will come. Same diagram, whatever it is written here. So first is direct stresses due to pre-stresses or pre-stressing force. How much it is? Direct stress. It is 4.95. 4.95. 4.95. Sign is plus on both sides. Plus what next? Bending stress due to pre-stressing force. Here we have the nature of stress. Same nature of stress. Minus and plus. So that answer we got as 4.95 only, same answer. 4.95 plus. What next? Self-weight stress. Self-weight stress we got it as 2.16. 2.16. and 2.16 positive, negative. Then movement, the stresses due to live load. The same nature of stress here, whatever same nature of stress I'm writing here. So here 9 and 9 plus minus, okay, is equal to, okay, this is stress due to pre-stressing force or pre-stresses. This is self-weight stress, self-weight stress. Then live load stress. Now you can write the resultant stress diagram. The nature of resultant stress diagram depends on the value which we got. Okay, here at the top fiber we got positive sign, which is nothing but compressive. I'll write the reference line now. I'll write the reference line. At the top fiber we got plus 11.16, plus 11.16. At bottom fiber we got minus 1.26. Okay, just join both the points. You will get the nature of stress distribution for the resultant stresses. Here it will be at the top fiber plus 11.16. At bottom fiber it is minus 1.26. Okay. So this will be resultant stresses. Okay. So this completes the problem. Very simple. If you remember properly this concept, okay, stress distribution concept, or if you remember properly all these stress distribution diagram along with their respective formula, you can easily solve the problems. You can easily solve the problem. This completes the problem. If you have any kind of doubt, okay, in any calculation, you can ask students. Any doubt in this? Any doubt? Friends? Okay, I hope it's clear for everyone. Now I'll move on to the next problem. Okay, next problem. Second problem. Okay, I'll be sharing the soft copy of the notes later. Okay, I written the notes. I'll be sharing it later in your group. Now we will solve the second problem. You just go through the problem. A unsymmetrical I-section beam is used to support an imposed load of 2 kN per meter. Live load is given. Okay, live load is given over a span of 8 meter. Length of the beam is given. It is given as 8 meter. The sectional details are top flange 300 mm wide and 60 mm thick, bottom flange 100 mm wide and 60 mm thick. Okay, the sectional dimension of the I section is given. Thickness of the web is given as 80 mm. I'll write the figure for the same. Top flange he says that 300 by 60. Bottom flange he says that 100 by 60. Okay, overall depth is 400. I'll write the figure for the same. Top flange 300 by 60. 300 by 60 mm. Bottom flange is 100 by 60. 100 by 60. Hundred by 60. Okay. Then what else is given? Overall depth of the beam is 400 mm. Overall depth is given as 400 mm. Overall depth of the beam 400 mm. Then at the center of the span, the effective prestressing force of 100 kN is located at 50 mm from soffit of the beam. Okay. The prestressing force is located at 50 mm from the soffit of the beam. I'll write the prestressing force location. So here, somewhere here, the prestressing force is located, and distance of that prestressing force is at a distance of, it is how much? 50 mm from soffit of the beam. So this is the prestressing force location. Okay. And the magnitude of the prestressing force is given as 100 kilonewton. Okay. Estimate the prestresses at the center of the span section of the beam for the following load conditions. One is, first combination is prestress due to sulfate. Second combination is prestress. First combination is prestress plus sulfate. Second combination is prestress plus sulfate plus live load. Okay. So here prestressing force, how much it is given? 100 kilonewton. I'll write here. Prestressing force. Same thing we have to calculate as we have calculated for the previous problem. No, same parameters we have to calculate. We have to calculate prestressing force. No need to do the calculation here. It is directly given. Okay, it is directly given. 100 kilonewton located at 50 mm from the bottom of the beam or soffit of the beam. Okay, at prestressing force we have to calculate area of the cross section. We have to calculate. Okay, then section modulus we have to calculate. Then moment due to live load, moment due to dead load. Then calculating the resultant stresses for these two combinations. That is prestress due to sulfate and prestress due to Two combinations, that is prestressed plus sulfate and prestressed plus sulfate plus live load. Okay. Initial data required is prestressing force, that is directly given. Prestressing force, that is directly given in the problem. P is equal to 100 kilonewton, that is 100 into 10 power 3 Newton. Okay. Then P by A, area is required, area of cross section, area of cross section. So there was an office call. Area of cross section. Cross section A. Okay. See, this is the type of section given in this problem is an I section. Correct? There is an I section. You need to calculate the total area of this I section. So all the dimensions of the I section are given. Correct? Using all these dimensions, you can easily calculate the total area of the section. Okay. Now, for calculation purpose, what I will do is I will divide the I section into 3 parts. Okay. I'll divide the I section into 3 parts. This I'll take as a rectangle number 1. Okay. This I'll take it as rectangle number 2. This I'll take as rectangle number 3. Okay, for calculation purpose. Now, total area of the I section will be equal to area of rectangle 1, 2 and 3. Sum of area of rectangles 1, 2 and 3. It will be A1 plus A2 plus A3. Okay. So area of rectangle 1 is 100 into 60 plus A2 is the area of rectangle 2. Thickness of the web, it is given now in the problem. Thickness of the web is 80 mm. I forgot to write it here. I'll write it now. 80 mm. Okay. So A2 will be area of this web portion. Area of web portion, how will calculate? Width is 80 mm. Depth is, it will be 400 minus 60 on either side. So how much you'll get? You'll get 280 mm. Okay. You'll get 280 mm as depth of web portion. So it will be 80 into 280. 80 into 280 plus area of rectangle 3. 300 into 60. 300 into 60. By this we'll get the total area of the section. How much you'll get? You check the answer. 46,400 mm square is the area of cross section. Okay, 46,400 mm square is the area of cross section. Then P is over, A is over. Then what next is required? You require the section modulus, correct? Section modulus is calculated as I by Y. Okay, I by Y, where I is moment of inertia, Y is the distance of centroidal axis from the bottom or from the top of the wave. Here you can see that whatever the section given, it is not symmetric about x-axis. Am I right, students? If I write the centroidal axis here, if I write centroidal axis here, the centroidal x-axis, it is not dividing the figure into two equal parts. Okay, so in the previous case, it was rectangle, it is centroidal axis distance y, it was directly d by 2, but in this case, it is different. Okay, yb will be different. It will be different, means distance of centroidal axis from the bottom fiber, it will be different. If it is a rectangle, it is directly total depth divided by 2. It is an unsymmetric section. That is why you have to calculate this YB. You have to calculate centroid of this I section from the bottom fiber, or else you can also calculate centroid of the section from top fiber. Okay, I will be doing the calculation with respect to bottom fiber only. Okay, therefore the YB, what is the formula for calculating the centroid? YB is equal to or location of centroid from bottom. YB, what is the formula? YB is equal to, or Y centroid is nothing but sigma AY by sigma A is the generalized formula. Here we have total 3 components. So the formula will be, if we expand this formula, it will be A1Y1 plus A2Y2 plus A3Y3 whole divided by A1 plus A2 plus A3. Okay, there are 3 components. With respect to 3 components, I have expanded this formula. Okay, I have expanded the formula. Now you calculate all these values: A1, A2, A3, and Y1, Y2, Y3. A1 you calculate first. A1 is equal to area of rectangle 1. It is 100 by 60. 100 by 60. So 6000 mm square. Then A2 is area of rectangle 2. It is 80 by 280. 80 by 280. If you calculate, you will get answer as 22,400 mm square. Then A3 will be equal to area of rectangle 3. A3 will be equal to 300 by 60. 300 into 60. If you calculate the answer, it will be 3 into 6, 18,000 mm square. Okay. Then what else is required? Y1, Y2, and Y3 is required. Y1 is equal to, what is Y1, students? Y1 is distance of centered of rectangle 1. Okay, distance of centered of rectangle 1 from base Y1. How much it will be? It will be 60 by 2 directly. It will be 60 by 2, 30 mm. Then you calculate Y2. Y2 is nothing but distance of centroid of rectangle 2. Okay, distance of centroid of rectangle 2 from base Y2. Distance of centroid of rectangle 2 from the base. How will calculate it? How will calculate it? You want distance of centroid of rectangle 2 from the base. So it will be from here to here, it is 60 plus depth divided by 2. 60 plus 280 by 2, if you do, you will get distance of centroid of rectangle from the base. Okay, so 60 plus 280 by 2. 60 plus 280 by 2. The answer is 200 mm. Then y3. Okay, what is y3? Distance of centroid of rectangle 3. Okay, somewhere here. Distance of centroid of rectangle 3 from the base. This is y3. How we will calculate again? You can calculate either as 60 plus 280 plus 60 divided by 2 or overall depth 400 minus 60 by 2. In both way you can calculate. In both way you can calculate. Okay. So I will go from bottom only. So 60 plus 280 plus 60 by 2. Okay. 60 plus 280 plus 60 by 2. 60 plus 280 plus 60 by 2. Answer is 370 mm. Okay. Therefore, YB, you can calculate the YB now. Substituting all the values, A1, Y1, that is 6000 into 30 plus A2, Y2, 22,400 into Y2, 200 plus A3, Y3, 18,000 into 370 divided by A1 plus A2 plus A3 or total area. Directly you can substitute 6,000 plus 22,400 plus 18,000. By this you will get YB. Okay, YB will get it as 244 mm. Check the answer, please. You will get it as 244 mm. Okay. So to this, we'll stop the class and we'll continue in the next class.